Hello everyone and welcome to our calculus notes for section 4.1 antiderivatives and indefinite integrals. So suppose we do the reverse of differentiation. Given a function, we find another function whose derivative is the given function. This is called antidifferentiation, and it's part of the larger process of integration. Now integration, the main topic of this chapter, is the second main branch of calculus, the first being differentiation. And together, differentiation and integration come together to form what we know as calculus. We will see that integration can be used to find the area under a curve over a closed interval, which has many important applications. But first, let's talk about antidifferentiation. So antidifferentiation is the process of differentiation in reverse, anti. So given a function f at x, we determine another function f at x such that the derivative of capital F at x is lowercase f at x. Okay, so basically, the derivative of capital F at x equals f at x. That means that this is the antiderivative of f at x. All right, so for example, let f at x equal 2x. The function capital F at x equals x squared is an antiderivative of f at x since the derivative of that x squared is equal to 2x. However, other functions also have a derivative of 2x. For example, x squared plus 1, x squared minus 2, and x squared plus 2 also differentiate to 2x. The x squared part differentiates to 2x, and the constant term differentiates to 0. So when you look at this, the plus 1, the minus 2, and the plus 2 really don't have any impact on the derivative, just the x squared part. Therefore, an antiderivative of f at x equals 2x is any function that can be written in the form capital F at x equals x squared plus c, where c is some constant. It can be any number. It can be 5, 7, a million. This leads us to the following theorem. The antiderivative of f at x, lowercase f at x, is the set of all functions capital F at x plus c such that the derivative of capital F at x plus c is equal to that f at x. Now that constant c is called the integration. Now if we look over here, this kind of shows us all the family of functions for x squared. So this is like x squared plus 3, this is x squared plus 1, x squared minus 2. And what you'll notice about all of these is they all have the same slope at the same x value. Doesn't matter where you go. If you're at x equals -1, you can see they all have the same slope there. And so really what we're looking at is that constant of integration, that plus c, as being the difference in the height only, not necessarily the shape or how steep the slope is. So let's do an example. Let's find an antiderivative, capital F at x, of the function f at x equals 3x squared. So another way to think about this question is to say 3x squared is the derivative of what function? Well, we kind of have to think backwards on this. One way I like to do is to just start by writing capital F at x, because that's what we're looking for. And we think to ourselves, well, the derivative is x squared, and I know that the derivative is always 1 knocked down from the actual power. And so this should have been x to the third power. Well, now if I take that derivative, well, that 3 would have moved out in front and times what's there. And that's exactly what I have. And so this is actually the antiderivative. Now, we know this because we can check it, right? We can actually take the derivative of both sides, and it should work out fine. So the derivative of capital F at x should just give us our f at x. Okay, and then the derivative of x cubed plus c is going to be 3x squared. And so we know this worked out. Now, a differential equation is any equation that involves x, y, and most importantly, the derivative of y. Okay, so you got to have the derivative of y for it to be a differential equation. Now, the solution to a differential equation is the antiderivative. So in the case that we just went through, we could have said that dy over dx is equal to 3x squared. That's a differential equation. Now the idea is, the solution here is to figure out what y value we would have here so that the derivative of that y value would be 3x squared. And you can kind of see how that works. So d over dx of some y function has to equal 3x squared. And we did show that it's the derivative of x cubed plus c that gives you 3x squared. All right, so let's try it with example 2. It says give the general solution of the differential equation y prime equals 3. So we can see that this is differential because we have that y prime. And so we just have to think, well, if that's y prime, we want to find y. And in this case, it's going to be 3x and plus c. So again, we had dy over dx had to equal 3. And we're trying to find what that y value is. So d over dx of what function leads us to 3? Well, it has to be some sort of 3x. And again, that constant doesn't matter. So this is kind of the process of how we figure this out. So the integral is basically the same thing as the antiderivative, and it is the inverse of the derivative itself. And so just to see how this works, before and in first semester, we were learning out how to take derivatives. So the derivative of f at x equals x squared, we would use the power rule and we would get 2x here. So that is taking the derivative. Now, if you want to do the integral, well, that's basically undoing and going backwards. Okay? So how this works is we have that dy over dx that we've seen before, and if that equals 2x, we essentially want to solve for y. Now, the way we're going to do this is actually multiplying here by dx. Okay, that really, really tiny value that shrinks down to nothing. Okay, we'll multiply by that. That'll be gone. We'll be left with dy equals 2x dx. Now, at this point, we can't really divide by d. D isn't a number, and so that is not the inverse of the derivative. Instead, the inverse operation is notated this way, and that's an integral symbol. So if we take the integral of the derivative, that is the inverse. It undoes. So what I do to one side, I do to the other side. And so what I'm left with now is y equals the integral of 2x dx. All right. So how do we go about figuring this out? Well, let's take a look a little more closely at indefinite integration. Now, an antiderivative is what we were just looking at. It's basically the same thing as an indefinite integral. Okay, it's the solution to that differential equation, and it's indefinite because you have the plus c part. Okay? Now, antidifferentiation is the process of indefinite integration. Those two words are the same thing. So the process of finding all solutions to a differential equation is the antidifferentiation process. It's basically the inverse of differentiation. Now, when we differentiated, these are the notations we used. So we started with f at x, and its derivative was f prime at x. Now, when you integrate, you actually go the other way. So if you start at f prime at x, its antiderivative will be f at x. And if you start at f at x, its antiderivative will be capital F at x. See why we needed the capital F at x? Because if you start at f at x, the function, you got to go up to capital F at x. So our notation here is the antiderivative of f at x with respect to x. So you have the integral sign, you have the integrand, that's the function on the inside, which is basically our derivative. Then you have dx with respect to x, and that's the variable of integration. Now the solution, we call this the general antiderivative. So just figure out the antiderivative, and then you have that plus c, the constant of integration. So we're going to take a look now at how to find these indefinite integrals a little bit quicker and easier. So in example 1, it says determine the indefinite integral. So here we have the antiderivative of 2x cubed with respect to x. So another way to think about this is 2x cubed is the derivative of what function? 2x cubed is the derivative of what function? So that's the derivative in there. Now we're going to look at the power rule for derivatives here to help us answer the question. So if we have a power function, y equals ax to the n, its derivative dy over dx we learned was, well, move the power out front, times what's there, and knock the power down 1. So that is the derivative of the power function. Now what we're saying is that 2x cubed is the derivative of some power function. And so we can just say dy over dx equals 2x cubed. Now in this case, 2x cubed has to equal our general form, n times ax to the n minus 1, the power rule. Now from this we can actually get a couple different equations. The 2 has to equal n times a, and the 3 has to equal n minus 1. See right up here, the 2 has to equal n times a, and the 3 has to equal n minus 1. Now when you go to solve for this, you can't solve n and a right away. You have to start on the right side here, and to solve for n, we would add 1 to both sides. So we get 4 equals n. Now we can substitute in there to figure out what a is. So 2 equals 4 times a, and we're going to divide by that 4, and we get a equals 1/2. So what we know is y equals ax to the n power. Okay, and so we can just substitute now. A is 1/2. We have x, and n has to equal 4. And so we know this antiderivative is going to be 1/2 x to the 4th power, and then don't forget the plus c. Now you might be thinking, hey, that's what I did in my head. I always add 1 and then divide by the new power. And you're exactly right. That is the power rule for integration. So if you have an antiderivative of a power in the form ax to the n, you basically raise the power by 1 and then divide by the new power. Okay, so we keep the a there. We raise the power by 1, so n plus 1, and then we divide by that new power, which is n plus 1. And of course, don't forget the plus c. Now there is one note here, that n cannot equal, well, what would make the denominator 0? Ooh, a -1. So this works for every power except when n is -1. So in that case, look what happens. Okay, we would have something like this, and the power rule doesn't work here because we get divided by 0. So instead, if I rewrite it like this, maybe that will help. If it's 1 over x, so 1 over x is the derivative of what function? So the derivative of what function equals 1 over x? Now if you think back to our derivatives, this one was the natural log of x. And so this antiderivative is going to be the natural log of x plus c. So you notice it's not power rule, it's something totally different. We're going to be looking at this more a little bit later on. All right, so we have some integration properties to talk about here. The antiderivative of 0. Well, what function has a derivative of 0? Well, that's going to be a constant function. So you get c there. The next one is k dx. So k is just a constant, and so that one is going to be k times x plus c. Now, if you have a constant multiple like k times f at x, that constant multiple just gets pulled outside of that integral sign. Okay, so that constant multiple in any of these integrals just kind of tags along through to the end and in the answer. Now our next one is plus or minus. So when you're adding or subtracting two functions, you can basically take the antiderivative of each one separately and then add or subtract them together. Okay, so this is good for polynomials with multiple terms. You can just split them up and do each one individually. Now, what you'll notice is that we do not have a rule for a product of two functions. Okay, so there is no product rule. We have to kind of find other ways of solving these. So if this is your derivative, f at x times g at x, what was the original function? Sometimes you can actually multiply these two together to get something you can use the power rule with, or there are some other complicated measures that we can talk about later. Now there's also no quotient rule. So if you have f at x divided by g at x, we have no quotient rule either. Now this doesn't mean we can't find these antiderivatives or indefinite integrals. It just means we can't use the power rule and there is no specific quotient rule for this. A lot of times we'll actually try to divide these two to get things that are power rules. And if you can't, you might have to manipulate them some other way. All right, so let's go ahead and give this some practice here. So the antiderivative of 4 dx, that one's just going to be 4x plus c. Now, if you want to check your answer by differentiation, we could differentiate both sides of this. And see what happens. So the derivative of the integral undoes itself, and we're left with 4. So that is the derivative. And then the derivative of 4x plus c should equal 4, and it does. And so that checks there. For number 2, all right, if you just have the antiderivative of dx, you don't have nothing there. You actually have 1 dx there. And so this is kind of a hidden constant in there. And so this ends up being 1x plus c, or just x plus c. And we're not going to check that one with differentiation. All right, looking at number 3. So again, this isn't a power rule. And notice that constant multiple in front, the 5, is just going to multiply in there. We're going to raise the power by 1, divide by that new power, and don't forget the constant of integration. So we get 5x to the 8 over 8 plus c. Now, if we check this derivative here, the derivative of 5x to the 8th over 8, we should get 5x to the 7th. Okay, and notice the plus c will differentiate to 0. So the 8 will go in front and times what's there. Knock the power down 1. The c goes down to 0. And notice the 8 over 8 cancels. And what are we left with? 5x to the 7th, which is what we were looking for. All right, so you can always check your answers just by doing the derivative. Let's try example 4. We have the antiderivative of 4 over x squared. Now, we said there was no quotient rule, so this fraction kind of can cause a problem for us. We need to rewrite this as a power function. So the way we do that, just like we did before, move the exponent into the numerator by making it negative. So you have 4x to the negative 2. And this is going to work just great. We'll keep the constant multiple of 4. We'll add 1 to that exponent. So we get negative 2 plus 1. We'll divide by the new exponent, negative 2 plus 1. Now, you don't actually have to show that plus 1 every time. I just did, so you know where it came from. And so this will be 4x to the negative 1 over negative 1. Ooh, and don't forget the plus c. Got to have that plus c in there. All right, technically I should have put it right here for this to be correct. Now we are going to simplify this. So the 4 divided by negative 1 is really negative 4, and the x to the negative 1 is really x to the first in the denominator. So this will be negative 4 over x plus c. All right, if we want to check that derivative, okay, we have the derivative of negative 4 over x, okay, and the plus c. Notice we have to rewrite it first as negative 4x to the negative 1. And now we can use our power rule, so negative 1 times negative 4 is 4. We'll knock that power down 1. Derivative of the constant goes away, and we get 4 over x squared, which again is what we were looking for. So that definitely checks out. All right, looking at number 5. So here we have a bunch of terms added and subtracted together. So we can just take the antiderivative of each one and then just put them all together. So 3x to the negative 5 would be 3x to the negative 4 over negative 4. We have minus 7x to the 4th over 4. So add 1 to the exponent, divide by the new exponent. Minus x, so this was x to the first, it will now be x squared over 2. And then plus 3, that one's going to be plus 3x, and then plus c. Now the 3 to the 3x, you might think, oh, I have to memorize that. How's that going to work? Well, it actually is the power rule. If you think about rewriting 3 as 3x to the 0 power, because x to the 0 power equals 1, 3 times 1 is 3. you could actually use that power rule now because you would get 3x to the first over 3, which is just our 3x. And so you can see right there that that's how we get that with the power rule. All right, let's take a look at number 6. This will also work for radicals. Okay, again, we just have to rewrite this as x to the 1/2 power with respect to x. And so now when we take that antiderivative, we can add 1 to 1/2 and get 3/2. Divide by that new exponent, so divide by 3/2. And then plus c. Now we usually don't like to leave this divided by a fraction, so we are going to multiply by the reciprocal and get 2/3 x to the 3/2 plus c. And sometimes you're going to see this as 2x to the 3/2 all divided by 3 plus c. So you might see that combined into one fraction there. All right, now number 7, here is another quotient of two functions. And in this case, just rewriting it isn't going to be helpful. We're going to have to do more than that. And so in this case, when you have a single term, the best thing to do here is go ahead and actually divide before trying to take the antiderivative. And so let me show you what I mean by that. We can actually do x squared divided by x squared plus 1 divided by x squared. All right, and this now allows us to rewrite this as the antiderivative of 1 plus x to the negative 2. And I believe we've done both of those already. Okay, so the antiderivative of 1 is just going to be x, and x to the negative 2 will be x to the negative 1 over negative 1, and plus c. And then finally, simplifying here, you would get x minus 1 over x plus c. Okay, no need to add these back together. You could, of course, if you wanted to, with common denominators. All right, number 8. So here we have 1 divided by x. If we try rewriting this, notice what happens. This becomes that x to the negative 1. And we said it can't work. Well, remember, if we add 1 to that exponent, and we divide by that, notice we get x to the 0 over 0. And this is just an indeterminate form. It's not helpful at all. So remember, the antiderivative of 1 over x is just going to be the natural log of x plus c. All right, our last topic for the day is initial conditions and particular solutions. So what we're going to do in this case is take that plus c and actually figure out what it is, because we're going to learn what a point on the original equation was. And so we're going to use the point and the slope, or the point and the derivative, to actually figure out what the original equation is. So thinking back to Algebra 1, can you find the equation of a line given a point and its slope? Well, yeah, you could use point-slope form, but remember, we have this general equation, y equals mx plus b. Do you remember what the m stood for? M was the slope, and then the b is the y-intercept. Now, in order to do this, you have to know a point. In this case, we know 1, negative 2. And so what we can do is we can plug in the m, we can plug in the x and the y, and then solve for b, right? So my y is negative 2, my m, or the slope, is 3, and my x value here is 1. And that allows me to solve for b. So we'll just subtract 3 over, and b is negative 5. And so now we're going to back substitute. We're going to keep the y, the m is 3, and then b is negative 5. Okay, so y equals 3x minus 5 is the equation of the line with a slope of 3 going through the point 1 comma negative 2. Now, something that's interesting here, if you look at that mx plus b, and that's a y equals, well, if we were to think about what y prime was in this case, wouldn't that just be m? Yeah, it's the slope. Slope and derivative, it's the same thing. So watch what happens. If I were to integrate the slope, m, with respect to x, what would I get? I would get mx plus c. Oh, that c and the b are actually the same thing because it just stands for a constant. And so because you know the general solution for every line is y equals mx plus b, you didn't even have to think about the antiderivative. But you can determine a particular solution for the equation given an initial condition and the slope of the line. And that slope of the line is actually the derivative of whatever function or equation we have. So in the general antiderivative, capital F at x plus c, that constant of integration c could be of interest in some applications. In such cases, if we know a point that is a solution of the antiderivative, it allows us to solve for c specifically. And this point is called an initial condition. So in order to solve the differential equation for the particular solution with the initial condition, we want to find that general solution of the differential equation. Basically, we want to integrate the slope to get that general equation. Then we substitute our initial condition, so our point x comma y, in the original equation, and we plug it into the general solution, and then we solve for c, and then plug that back in and rewrite. All right, so let's give this a try here. So it says find a particular solution for the equation having a derivative of capital F prime at x equals 2x plus 3 with an initial condition of capital F at 1 equals negative 2. All right, so we're going to be looking for f at x, and we're going to want to eventually solve for c. So what we need to do is integrate the derivative. Okay, and so this is the antiderivative that we've been working with. So it'll be 2x raised to the power 1 to squared divided by a 2. So it really becomes x squared and then plus 3x plus c. And we want to solve for that c value right there. So we're going to have to plug 1 into my x values and set that equal to negative 2. So negative 2 equals 1 squared plus 3 times 1 plus c. So a little bit of solving here. Well, it looks like we'll subtract 4 and get negative 6. So c equals negative 6. And all we do is go ahead and plug that back into our antiderivative. So x squared plus 3x minus 6. All right, so that is the particular solution with the initial condition. Now, when you're given a second derivative and asked to find the solution to the differential equation, you actually have to go all the way back twice to get to the original function. So you have to go from f double prime to f prime and then f prime to f. So you actually have to have two initial conditions here, one in the derivative and one in the original function. So here, the second derivative is equal to negative 2. So I'm going to have to do this twice. First, let's find f prime at x. So that's going to be the antiderivative of f double prime. And so the antiderivative of negative 2 dx, which is negative 2x plus c. We need to find that c, and I know that f at 2 is equal to 3. All right, so 3 is going to be negative 2 times 2 plus c, and we'll add 4 over, get 7 equals c, and so f prime at x is going to equal negative 2x plus 7. But I want to get all the way over to the original function, f. So now f at x is going to be the antiderivative of f prime. So that's negative 2x plus 7. All right, and so we're going to go ahead and figure this out. So negative 2x raised to the power 1 be squared divided by 2. So it's really negative x squared. And then 7 will turn into 7x. And we have plus c. Well, let's go ahead and solve for c. And in this case, I know that f at 2 equals negative 1. So I'm going to plug 2 in here and set that equal to negative 1. All right, and a little bit of solving. Watch the negative there. Negative 1 equals 10 plus c. And so c equals negative 11. And so f at x really equals negative x squared plus 7x minus 11. All right, so not any more difficult when you are started with the second derivative. You just have to do the process a couple times there. All right, now the antiderivative of a function has many applications. So for example, velocity is the derivative of a distance function. Remember that? So if you had a position equation s at t, the velocity would be the derivative of position. Okay? And so what that means then, inversely, the distance has to be the antiderivative of the velocity function. So if you know the velocity function, you can antiderive it to get back to the original position. So if we integrate here and here, you'll be left with just the s at t function. All right, now if information about the distance of the object is provided at some time t, if you know that, then you have that initial condition. So in our example, a rock is thrown directly upward with an initial velocity of 50 feet per second from an initial height of 10 feet. The velocity of this rock is modeled by the function v at t equals negative 32t plus 50, where t is in seconds and v is in feet per second. And t equals 0 is going to represent the moment the rock is released. Well, it turns out that velocity function is also found using an antiderivative. So the antiderivative of acceleration is going to be velocity. So in this case, we know acceleration due to gravity is negative 32 feet per second. So check this out, negative 32 dt. That antiderivative will be negative 32t plus c. And notice the initial velocity is going to be 50. That's v at 0 equals 50. We can say 50 is equal to negative 32 times 0 plus c. And that zeroes out, so c equals 50. And our velocity function is negative 32t plus 50. All right, so that's how they got that negative 32t plus 50. Now let's go ahead and determine a position function off of this velocity. So our position function, s at t, is going to equal the antiderivative of velocity, which was negative 32t plus 50. And that's now with respect to time, because time is our independent variable. So we'll go ahead and do the antiderivative here. Keep the constant multiple, raise the power 1, divide by that new power. And then 50 will become 50t. And then we have plus some constant. And I'm going to divide 32 by 2, so get negative 16t squared plus 50t plus c. And let's see what our initial position is. So the initial height of 10 feet. So that's s at times 0 equals 10. And so I'm going to set 10 equal to a time of 0. So negative 16 times 0 squared plus 50 times 0 plus c. And notice these zero out, and c is going to equal 10. So my position function is going to be negative 16t squared plus 50t plus 10. All right, so from this now we can actually determine the height after 3 seconds and the velocity after 3 seconds. So s at 3 will be negative 16 times 3 squared plus 50 times 3 plus 10. And this turns out to be 16. So we know it has to be 16 feet high after 3 seconds. And then the velocity came from our velocity formula, which is negative 32 times 3 plus 50. And this turns out to be negative 46. So the negative just means that it's coming back down, okay? And so we're going to say it's dropping at 46 feet per second at time equals 3. All right, so that is antiderivatives, indefinite integrals, and then specific answers given initial conditions. All right, thanks for watching.